We now have Professor Arvind Pattamatta from IIT Madras. Professor Arvind Pattamatta is a professor in the Department of Mechanical Engineering at IIT Madras. He earned his PhD from SUNY and is renowned for his work in energy transport, thermal management, and computational fluid dynamics. His research spans microscale energy transport, phase change heat transport, and thermal management of electronics and batteries. With over 140 peer-reviewed publications, Professor Arvind Pattamatta is a recipient of prestigious accolades, including the Alexander von Humboldt Fellowship in 2013, INAE Young Engineer Award in 2016, and JSPS Invitational Fellowship in 2007. He also serves as the Secretary of the Indian Society for Heat and Mass Transfer. Today, he will discuss the influence of surface wettability and patterning on phase change, heat transport, and passive cooling systems. I welcome Professor Arvind Pattamatta to begin.
Thank you. So, hopefully I'm a little comfortable seated for talking. The recording is also fine. Is that okay? And I think the people also can see the screen from all sides. So, a very good afternoon or good morning. At the forum session. And we had very interesting talks before this related to thermal management in spacecraft and also something more fundamental topic of micro layer and contact evaporation model. So I'm here to talk about the role of or influence of surface wettability and patterning of surfaces on phase change heat transfer, primarily focusing on the passive cooling systems. And of course, this is a joint work of many of my past PhD students, postdoc, and also Professor Pallav, who is a co-PI in this project for a long time. So, as Simhachala Rao already shared the slide, there is an interesting slide about what is the need for effective thermal management. So, we know that the rapid miniaturization of electronics is called for looking at high performance cooling techniques, and most of these, in fact, there was a study by the US Air Force Avionics Security Program that they identified out of the total equipment failures, nearly more than 50% of the failures were attributed to hot spots at high temperatures. Of course, the other parameters being vibration, humidity, and dust, and so on. And this figure right here shows how the heat fluxes of these microelectronic chips have gone up dramatically in the last 3 decades or 4 decades. And you can see some of the latest Intel i9 processors have approached or crossed 100 watts per centimeter square of heat flux. So that is the kind of heat dissipation nowadays that we. And if you look at data, we see that 40% of the total power consumption goes in data centers. So this calls for basically energy efficient chip level cooling systems that we can fundamentally address the heat dissipation in the chip level rather than doing it at a much larger scale. And now if you look at the different solution strategies for effective thermal management, of course, conventionally using forced convection of air or liquids, and they are limited by, as you all know, the heat transfer coefficient of single phase systems are fairly limited. And when you move on to phase change heat transport using boiling and condensation, you can go up to 2 orders of magnitudes of higher heat transfer coefficient as compared to single phase convection. So therefore, cooling devices that employ phase change heat transfer are therefore desirable for more effective thermal management. And when we talk about phase change, again, you can either talk about, or even single phase, we can use passive cooling or active cooling, as Dr. Simhachala Rao has briefly introduced. So, for example, you can use a microchannel or a conventional heat sink with fins, and use natural convection, combination of conduction, natural convection, and radiation to cool the component which is attached to this heat sink. Whereas you can also use a fan which is blowing the air, and this is actually a same heat sink, but now we use a forced convection, and therefore it becomes an active cooling mechanism. Apart from that, from the passive two-phase point of view, we have heat pipes, so which are essentially devices operating between the heat sink and the heat source and heat sink. So the heat source is attached to the heat dissipation devices like this, and you have a capillary wick structure inside, so which basically pumps the liquid from the condenser section to the evaporator section. I'm sorry, this should be the blue one should be the condenser, and the red one is the evaporator here. So that this can operate under any orientation and even under gravity. And now a modification to these will be to use pump, so that you can use mechanically pumped cooling solutions between the evaporator and condenser to enhance the rate of heat dissipation. So these are some of the different classifications based on whether you use an external energy source or not. Now, my talk will be mostly focused on passive cooling systems such as the heat pipes and thermosiphons. And the conventional heat pipe, I think most of you know, is operating between a heat source and a heat sink. And we generally see that due to the evaporative action, the vapor, due to the higher vapor pressure, gets transported towards the condenser side, where it dissipates the heat to the ambient through an external maybe a coolant or air which is used, and then the condensate will be returning back to the evaporator based on the capillary pumping of the wick. The wick structure therefore plays a very important role in making sure that this device can operate even under gravity or microgravity conditions or any orientation. So, but if you do not want the wick structure to influence this transport, then the device has to be oriented in such a way that the evaporator is at the bottom, condenser is at the top, and the gravity is acting downward, and this becomes the classical two-phase thermosiphon. So of course the classical two-phase thermosiphon is quite efficient. You can go to very high heat fluxes, you can achieve boiling and so on, which is not so easily possible in a classical heat pipe where you have this porous wick. So it has a boiling limit there, so mostly it's driven by evaporation there. But here it is mostly confined to terrestrial applications, and you have to be conscious of the fact that the evaporator has to be at the bottom and condenser is always at the top. So therefore, we can now move on to more advanced heat pipes, which can work irrespective of the orientation of the evaporator and condenser, and which doesn't need a wicking mechanism. So these are called as pulsating heat pipes. So the working fluid oscillates when we fill when we evacuate the pulsating heat pipe and we fill this with working fluid. So we see that the working fluid forms liquid flux and vapor flux and liquid slux, and you see that these are the flux and slux which keep oscillating between the back and forth between the evaporator and condenser, that results in the effective transport of the heat from the evaporator to the condenser side. So, so what causes this oscillation mechanism? It's essentially a very complex thermohydrodynamic phenomena. So you require a temperature difference between the evaporator and condenser, which builds this pressure difference, and therefore this causes this oscillating and circulating mechanism. And there's a limit for the channel diameter. Of course, you cannot use any large size channel. So it's specified by the bond number criteria. And if the bond number is less than 4, it tells you that the surface tension is going to be a dominant force compared to your gravity or the buoyancy force. And typically, if you look at some of the modifications to this capillary tube PHP, when you want to adapt it to a more compact devices like electronics cooling, you make a flat plate pulsating heat pipe, wherein you take a copper substrate or a stainless steel substrate, and then you etch these mini channels or micro channels out of them, and then you can have the evaporator, adiabatic, and condenser blocks attached to these backside of these plate accordingly. So I've discussed about the thermosiphons. There are different classifications of thermosiphons and geometric modifications. The one that we will be focusing on is the horizontal flat thermosiphon, which I think also Simhachala was talking about, the use of flat thermosiphons or vapor chambers. So these are also very effective heat spreaders. So it results in spreading of high heat flux from a heat source relatively to a lower heat flux. It's a flux transformer basically, and also you have a filling of a fluid to a certain filling ratio, which results in also phase change mechanisms like boiling happening within the fluid, and then the vapor going to the condenser side and condensation happening there, and the condensate can actually accumulate and they can fall down back into the pool of liquid. So this is also a very effective mode of passive heat transfer device. In this case, since we are not having any wicking structure, so this is a classical thermosiphon, and again you can achieve very high heat fluxes due to the you can go to high heat fluxes, and boiling can be very effective in this case. So what I'm going to talk about is how we can use surface wettability as a tool to probably improve the evaporation or the boiling and condensation phenomena that you come across in these passive heat transfer devices, and try to improve the performance of these thermal management devices. So I think many of you have some basic idea about the surface wettability. So when we talk about wetting, this is the ability of the liquid to basically maintain contact with the solid surface, and this results from the intermolecular interactions when you have liquid coming in contact with the solid. And if you do a small experiment where you place a drop of water on a surface, so there are actually different interfacial tensions that are acting. So the interfacial tension between the solid and the water molecule, and you have the interfacial tension between the solid and the gas, and between the liquid and gas, which we call as the surface tension force. So all these interfacial tensions in equilibrium decide what is the apparent contact angle that this water drop makes with the surface, and it is given by the famous Young's equation. So you can measure your equilibrium contact angle and try to basically validate. If you know the surface interfacial tensions, you can validate whether the contact angle from this expression, Young's expression, matches your experiment or not. And of course, things are not as simple as just measuring the equilibrium static contact angle. So you also have basically advancing and receding. There is a contact angle hysteresis, and you can also use techniques to measure the advancing and the receding contact angle, and also deviations from this. When you basically tilt a surface, there is a certain critical threshold beyond the angle the droplet can actually roll off, and then the angles become dynamic. So the advancing and the receding contact angles become function of the velocity, the capillary number of the interface which is moving along the surface. So therefore, these are very complicated phenomena that if you want to study in isolation, you can do that. But then how do you use this wettability in favor of improving the boiling and condensation performance in these thermal management devices? So I think this classification all of you are familiar. So we talk about contact angles. These are equilibrium contact angles, by the way. Less than 90 degrees generally termed hydrophilic, and anything less than 10 degrees is called a super hydrophilic surface. And hydrophobic surfaces are classified based on contact angles which are above 90 but less than 150, and then those angles which are above 150 but less than 150, 180, these are called super hydrophobic surfaces. And again, you can have a non-sticky versus sticky depending on the contact angle hysteresis of these surfaces. So if you have basically larger contact angle hysteresis, so you can even have tilted to 180 degrees, the substrate, and you still see the droplet is intact. So this is called the Pittel effect. Whereas in a lotus effect, if you tilt a little bit due to the low contact angle hysteresis, there is a roll off of these droplets. So within the super hydrophobic surfaces, you have therefore both sticky and non-sticky regimes. Now, when it comes to what is the role of surface wettability on boiling, I think this was a very interesting paper from Justin Wiebel and Garimella 5 years ago. So where they have showed, of course, there have been numerous studies on what different types of surfaces do to enhance the pool boiling. So typically, if you take a reference sample, which is copper, which has an equilibrium contact angle of 52 degrees, it's hydrophilic, and it has reasonably high contact angle hysteresis, and this is the kind of nucleation that you see. So you see that generally, if you tend to make the surface more and more hydrophilic, the nucleation becomes a little sparse, and the onset of nucleate boiling gets generally delayed because of the high surface affinity for the liquid. But once the onset of nucleate boiling is initiated, you see the nucleate boiling regime itself is sustained to a much longer duration, and the critical heat flux also can be enhanced due to this because of the improved rewetting characteristics. So you see the hydrophilic surfaces are therefore, or super hydrophilic surfaces are good in maintaining the critical heat flux to a higher value, and also the nucleate boiling regime considerably, but only problem will be the onset of nucleate boiling has to be a little bit delayed. Whereas if you go to hydrophobic surfaces, again, if you have hydrophobic surfaces and high contact angle hysteresis, the nucleation is quite rapid, but at the same time, you do not have a very quick transition to the film boiling. Whereas if you have a hydrophobic surface and a low contact angle hysteresis, so the transition to film boiling is very quick. So therefore, if you just compare a similar heat flux of 8.3 watt per centimeter square, the copper surface, which is hydrophilic, requires a slightly higher wall superheat to start the onset of nucleate boiling as compared to the hydrophobic surface, which has a high contact angle hysteresis. But then, if you even at lower heat fluxes, the hydrophobic surface with the low contact angle hysteresis goes very quickly to film boiling, and then you see the wall superheat has increased considerably higher. So therefore, the nature of surface plays a very important role on the boiling characteristic. Especially the pool boiling has been very well demonstrated in these experiments. So what about the role of surface wettability in condensation? Again, if you talk about most of these passive devices where you are evacuating and filling this with the liquid inside, so it's a pure single component system. So in these single component systems, we generally see that very effectively using super hydrophobic surfaces results in dropwise condensation, and these dropwise condensation is by far results in very high condensation heat transfer coefficients as compared to using super hydrophilic surfaces which promote film-wise condensation, which basically deteriorates your heat transfer coefficient. So this is quite good for as far as a single component vapor is concerned, but once you have a presence of non-condensable gases and so on, then the phenomena will be slightly different. So then the way that we have employed these techniques of surface treatment towards improving the boiling and condensation performance has been mostly by chemical etching. So we used different chemical etching processes. So there are actually, we first start with preparing a super hydrophilic surface, wherein we treat with sodium hydroxide and potassium persulfate. And we see the most common formation is an oxide formation of copper, which grows like a flower-like nanostructures, and the droplet is completely wetting the surface. And from this to go to a super hydrophobic surface, we treat it now with silane, which is FAS 17. And when we do this treatment with silane, we see the contact angle suddenly goes to a super hydrophobic value of 165 degrees and very, very low contact angle hysteresis. And we also found that this treatment with FAS 17 results in a very durable surface against thermal degradation. And now there are also other methods to achieve super hydrophobic surfaces using chemical etching. So one is with the stearic acid, and then treating it with nanoparticles. But then we found that these result in considerably larger contact angle hysteresis, and they are also not thermally as durable as the one with silane. Apart from that, we also tried electrochemical deposition or anodization processes for making the surface super hydrophobic, and we found that also results in a fairly low contact angle hysteresis. And we also tried laser texturing. So laser texturing using a nanosecond laser also can be used to create these super hydrophobic surfaces, but with a considerably larger contact angle hysteresis. So when we compared the equilibrium contact angle as a function of time, so we did basically a durability study over a couple of weeks to find out against thermal degradation how these surfaces or different treatments perform. We found that the use of sodium hydroxide plus the silane results in most stable surface treatment, followed by the anodization or the electrochemical deposition and the laser texture. So these three methods have resulted in a fairly stable equilibrium contact angle when we subject it to cycles of heating and cooling over 14-day period, whereas the other chemical etching processes rapidly deteriorated, and then within 14 days the contact angle came back to its original value. And these figures show the SEM images of the flower-like structures of these copper oxide formation. So you can see the details of this, and also the presence of the individual atoms or molecules of the chemicals that we treated to confirm that indeed these are attached to the surface. And apart from, so whatever I was talking about was basically the wettability aspect. Now using chemical etching processes. Now how do we, what do we do with the surface patterning? There is something that we can also talk about in terms of changing the morphology of the surface by patterning them. Like for example, you can use this micro nano pillared kind of surface. It looks like fins, but these are on much smaller scale of the order of microns, and sometimes so the order of nanometers as well. And you can also have sintered particles, so which can be deposited on these surfaces, so they also can change the nature of the wetting processes. And you can also have hierarchical structure where you can have this kind of micron size pillars, and then you can have a nanoscale roughness over them, so you can do a more detailed wettability modification using such kind of hybrid or hierarchical structures. So what do the surface patterning do to the wettability? So there are multiple effects. It's not just the wettability change. Of course, you have some enhanced wettability, but also they increase the total available surface area for heat transfer, and they also engineer the nucleation sites, particularly when it comes to boiling, and also they change the wicking capability. So a combination of all these aspects actually can result in a better boiling or condensation processes. And when we use this in thermal management devices, therefore we cannot attribute only to one factor which can modify this performance. So generally, therefore, there has been a lot of promise of using a combination of wettability modification using chemical etching processes as well as surface patterning for these thermal management devices. So I'm just going to quickly talk about a couple of devices where we employed these wettability modifications. So one is on the flat plate pulsating heat pipe. So as I already described the basic phenomena of a flat plate PHP, so it's a modification to the capillary tube PHP wherein the surface is much flatter and we etch mini channels onto these copper substrate. So on the back of this, we attach an evaporator block which mimics the heat generation device. And on the other side, we have the condenser device where we have a coolant which is connected through a thermostatic bath. And then the portion which is neither heated nor cooled is referred to as the adiabatic section, but we really do not insulate anything. So the idea is what do wettability modifications to the evaporator and condenser side of these flat plate pulsating heat pipe do to the performance of this? So we this is the experimental methodology. Of course, we evacuate the flat plate pulsating heat pipe, and then first we completely evacuate it using a combination of a normal pump, rotary pump, and a turbomolecular pump. And then we fill this working fluid. The working fluid we used was primarily water, and then we used a binary fluid of water ethanol, which is of the proportion 3:1. We tried different combinations, and we found that this was giving the most optimal performance for this. And we tried different filling ratios, and we found 60% is probably ideal. And we also varied the heat inputs from 40 to 200 watts. And once we fill this device, of course, there is a transparent cover plate. We can also observe the kind of oscillations that are happening inside these mini channels, and we can draw the regime maps of the operation of this device. So just to come for the results. So we have done different wettability combinations. So what we did was, this is the bare FPPHP where we didn't do any treatment, and the equilibrium contact angle as expected is around 78 degrees. This is copper. So this is with water. And then we did a treatment where we completely made everything super hydrophobic using the same chemical etching process that I described using silane. And that resulted in an equilibrium contact angle of 165. And then the other case, we completely made everything super hydrophilic using the chemical etching treatment. This results in complete wetting of the fluid. And the other one is a hybrid where we didn't treat anything for the evaporator and the adiabatic section, but we made the condenser section completely super hydrophobic. So we wanted to see whether the hybrid structure results in a better performance. So this is how it looks. Of course, I've explained the chemical treatment process, the etching, and then when we is completely super hydrophilic, you see that it spreads when we drop water on the surface. And for the once we make it completely super hydrophobic, you can see that the equilibrium contact angle is around 160 degrees. So So now these are some of the flow regimes that we observed when we operated the FPPHP with water at 60 watts and 60% filling ratio. And as you can see, the most suitable type of regime that we want is basically the slug plug oscillations, because primarily, as I said, the slug plug oscillations are the driving mechanism for effective heat transport in a pulsating heat pipe, and any deviation from this will always result in a lower thermal performance. So when we take the bare surface, we see that these mostly we have slug plug oscillations at the smaller heat fluxes, but at higher heat fluxes it's mostly kind of small droplets. It's not elongated slug plug, but smaller droplet oscillations. So this is what we see at 60 watts. And when we go to completely super hydrophobic surface, we see that it is mostly what we call as a Taylor droplet. It's slightly elongated, but not as much like what we see in a typical slug plug case. And at higher heat fluxes, it results in a complete evaporated dryout. Whereas if you take a combination of hydrophilic plus super hydrophobic, that is the hybrid configuration number 4 I was showing. So we see that evaporated dryout is happening even at lower heat inputs of 80 watts, so which is not desirable. Sorry, so there is some animation issue, looks like. Check. Last time. Because I think animations can problems. Yeah. Okay. So if I go to fully super hydrophilic evaporator and condenser, we see at 60 watts, this results in the maximum, prolongation of the slug plug oscillations, even at very high heat inputs of 200 watts. So the idea here is basically the use of completely super hydrophilic surface can result in the best performance. So we can see that it results in gives slug plug oscillations all the way from 40 watts to 200 watts here. So of course the same regime map holds well. I'm going to 160 watts to show you what happens to the oscillation process visualization. We see that as I said, if you are in 160 watts, you will need to dry out when you are in super hydrophobic or a combination of hydrophilic evaporator and a super hydrophobic condenser. Whereas with the super hydrophilic evaporator and condenser, it still retains the slug plug oscillation. As you can see, the slug plug oscillations are very evident. Whereas you can see both the hydrophilic and super hydrophobic combination and super hydrophobic throughout is completely leading to a dryout evaporator. So that means that with the modification to a fully super hydrophilic evaporator and condenser, we can retain these slug plug oscillations considerably, even to a maximum heat flux that we can apply. And of course, if you look at how they translate into the overall resistance of this device, because we measure the performance of these devices based on the overall resistance. The resistance is measured as a temperature difference between the evaporator and the condenser side to the heat that is supplied. And we find that the super hydrophilic evaporator and condenser case results in the lowest thermal resistance, which is not surprising, as we saw that the slug plug oscillations were dominating even at very high heat input, and therefore this clearly tells you that this is probably the best treatment for the pulsating heat pipe. And we also tested the durability of this performance of this wettability treatment on the performance over a period of 15 days, and we found there is some effect. Of course, there's a marginal degradation, but it still retains to some effect, the superior performance with the fully super hydrophilic surface. So we have to do tests, maybe more than 15 days to see what happens to this. So now the second example that I'm going to quickly talk about is on the wettability modifications as applied to a compact flat thermosiphon that I was also showing you in the beginning. So as I told you, the compact flat thermosiphon is basically acting like a heat spreader and also a heat transport device. So we have a discrete heat source which is attached to the bottom. This is your evaporator section. The heat is spread to the device completely by conduction, and also internally you fill it with working fluid. So there is also a possibility that you have a boiling happening inside, and then you have a condenser section on the opposite side. And in this case, we call this as a compact flat thermosiphon because we want to make sure that the thickness of this thermosiphon is as small as possible to make it usable in mobile friendly applications. And we have also done an extension to this compact flat thermosiphon to what we call as an integrated flat thermosiphon, wherein if you see some of these mobile applications or even in electronics cooling, these vapor chambers or flat plate thermosiphons, you also have to attach fins on top of it, and there is an additional resistance because of the thermal interface material that you employ to attach these fins. Rather, we wanted to see how do we integrate the fins directly onto the condenser. So these are like hollow fins, and at the same time we find that the condensation heat transfer also can be enhanced because of the hollow portion inside. So we thought that we should name this as an integrated flat thermosiphon. So I'm just going to talk about how we use the wettability in both compact flat thermosiphon and integrated thermosiphon to see the performance improvement. So we did some experiments on the CFT, just like the way we did for the PHP case, and we did different wettability combinations in the CFT also. For example, here you see there are 5 different wettability combinations. So CFT1 is a bare evaporator and a bare condenser, and then you have CFT2, which is bare, which is hydrophilic evaporator and a super hydrophobic condenser, and then you have CFT3, which is a super hydrophilic evaporator and a super hydrophobic condenser. CFT4 is a super hydrophilic evaporator and a bare condenser. So CFT5 is a super hydrophobic evaporator and a super hydrophobic condenser. So we did all possible combinations of wettability modifications for both the evaporator and condenser to see how the compact flat thermosiphon performs with these modifications. So we plot basically 2 resistances. One is the total resistance of the device, and the other is the spreading resistance, which is also important since it's acting like a heat spreader, to see how the wettability modifications influence each of these individual resistances. And we find that the resistance for the CFT2, so if you see, the CFT2 is basically the bare or hydrophilic evaporator and the super hydrophobic condenser, is giving you the lowest resistance among all the different wettability combinations. Now, if you compare this with what we did for the flat plate heat pipe, we saw that for flat plate heat pipe, completely super hydrophilic case, that is super hydrophilic evaporator and condenser, resulted in the best performance. Whereas in the compact flat thermosiphon, we see that a hydrophilic evaporator and a super hydrophobic condenser gives you the best performance. So therefore, whatever wettability modification that we can use for a flat plate PHP cannot be directly extrapolated to thermosiphon device because of the nature of the heat transport mechanism. So then what we did is to also ensure that we understand the pool boiling mechanisms with these structured surfaces or patterned surfaces. We wanted to study some basic pool boiling experiments using different types of mini channels. So we did 2 types of mini channels. One mini channel where the channel is of 1 millimeter by 1 millimeter cross section. The other in which it's 2 by 2, so square mini channel configurations. And then we found that the mini channels, use of mini channels results in a dramatic improvement in the heat flux for a given wall superheat, primarily because of the increase in the surface wetted area. So when we plot the heat flux based on the projected area, so you can see that there is a substantial improvement over the flat surface. The flat surface is these brown lines, and then you have the black lines, which are the second mini channel, which is of 2 mm by 2 mm. So they result in higher heat flux for the same wall superheat. However, when you plot these pool boiling curves based on the total wetted area, they all collapse on more or less on top of each other. So this tells you that the enhancement here is only due to the additional surface area or the fin effect, rather than additional nucleation sites provided by the use of these mini channels. However, I think there are also some papers by Kandlikar primarily where they tested microchannels and they found that for smaller channel sizes, the nucleation effects also can be improved and you can get enhancement even if you plot based on the total wetted area. So this is one interesting set of results that we got. And then we also went ahead and plotted what is the bubble departure frequency and the bubble departure diameter with these mini channels as compared to a flat surface. And we found there is some modest improvement. For example, the bubble departure frequency is slightly higher with the mini channels as compared to the flat surface, and the bubble departure diameter is also moderately lower for the mini channel surfaces. So there is also definitely some enhancement in the nucleation, albeit it is very, very minimal. So with this understanding of what these pattern surfaces can do in pool boiling, so we wanted to now integrate both the wettability modifications using the chemical etching and the pattern changes to the evaporator side, and we designed what is called as the integrated flat thermosiphon heat sink. So what we did here was we take evaporator, and then we introduce these mini channels on the evaporator side, and we integrated the fins directly into the thermosiphon, and then we made the fins hollow. And we found that when we do a super hydrophobic coating onto these hollow fins, we find that the dropwise condensation is also actively promoted into that. And also at the same time, this eliminates your interface resistance when you attach the fins externally. So now we have these different types of combination of the wettability patterning and the surface patterning and the wettability modifications. So, and when we tested these different surfaces, we found that the integrated flat thermosiphon 4, so which is basically the last right one here, which has these mini channel evaporated surfaces and a super hydrophobic condenser. So this results in the best performance. You see the overall resistance, the lowest for this device as compared to the other combination of wettability and surface pattern. So this tells that not only maintaining a bare surface for the wettability, but if you can improve this by patterning the evaporator by introducing these mini channels, you can additionally improve the overall performance of these devices. So to summarize, I think I'm more or less coming to the end of my talk. So to summarize, I mean, we have to be cautious when we apply these wettability modification techniques to different thermal management devices. So there is no one recipe which fits all. So especially for the flat plate pulsating heat pipe, we found that when the entire surface is super hydrophilic, this results in the best performance because it can maintain the slug plug regime even at very, very high heat inputs. Primarily because there the temperature difference is the driving force for the slug plug oscillations. So any disturbance to the driving temperature difference is going to inhibit the performance of these devices. Whereas when we use the surface modifications or wettability modification to a flat plate thermosiphon, we find that using a bare surface or rather a mini channel or micro channel surface for the evaporator and a super hydrophobic surface for the condenser results in the best performance because the evaporator and condenser are not in direct contact with each other, and therefore the classical link to enhancing your condensation performance there works very well for the condenser side. So with all this understanding now, I think we are a little bit better towards using these fundamentals in practical device design. So where we can try out, extrapolate these findings to also commercial devices based on, say, for example, vapor chambers, where we now have to introduce a wick structure. And because of that, we also have a boiling limit there. We cannot really go to the boiling case, but we have to make sure that the wettability modification works in the presence of these wick structures as well. So this is basically the next steps that we want to do in the near future. Hopefully, with that, I can conclude my presentation, and these are some of our published works, list of patents and journals that we have published from this in the last 5 years of work. And finally, acknowledgement to all the students and also the research collaborator from DRDO, Dr. Pankaj, and Professor Kallar, who is sitting here. He is the co-PA in this project. So it's a cumulative effort of all these people which resulted in this output. Thank you so much.
Yes, question. So in one of the chart shows that how this equivalent contact angle is varying with time. So it shows that up to 16
the durability.
Yes, it shows that up to 16 days the laser effect timing is not flat, but it's somewhat maintained. And but for other chemical etching, it is degrading very fast.
Right.
So when you apply this kind of technology in DLR application, for example, for electronic cooling, then your performance will decrease. We want the device to last for at least for 1-2 years, right? But performance will degrade after 16 days. Because I also get the same question several times.
In fact, even when I plotted this over 14 days, it's not exactly constant, but there is a slight deterioration in the equilibrium contact angle. And in fact, when we did this study on the FPPHP also, the durability shows that along with the equilibrium contact angle deterioration, performance is also slightly increasing over time. Resistance is increasing, which means there is a deterioration of performance. So the day 1 is giving the lowest resistance, and when we go to the day 15, it's slightly higher. Naturally, I think the durability of the surface is still not perfectly achieved here. I think this is one reason probably changing the surface wettability and using it for thermal applications, especially, has not been very well established till now. There's still an open question mark for research to see how we can create, from the materials point of view, surfaces which are more durable from the thermal perspective. Because there are numerous papers on how to modify wettability of the surfaces, but they have not tested it for repeated cycles of heating and cooling and in such kind of devices to understand whether these are durable under repeated thermal loads. I think this is one area probably we need to work with material scientists.
Moreover, this might be in a controlled atmosphere also, but when you take the practical aspect where the device is continuously exposed to higher temperature environment or humidity, this might further may get deteriorated.
Yeah, you're right, because we also have to should not expose it to ambient conditions. When after we finish the experiment, we need to keep it in a closed chamber, and as you said, if you leave it out, you disassemble and open it out, it may deteriorate faster due to the oxidation process. So definitely, the thermal durability is something that we need to work out, and when we get some materials and coming out with some kind of a methodology for changing this wettability, we also have to tell them to study this over a period of time with increased thermal loading and so on. That's how we get confidence in these kind of.
I might add something. We had a space experiment, built a space heat pipe 15 years ago. It was a copper water heat pipe. And there was a deterioration for about 4 weeks, and then it was stable.
And normal atmospheric condition.
We just we evacuated the heat pipe, then filled it with water. It was a copper thing, and we thought it would be oxidation. And then we pre-oxidized the copper heat pipe before filling it, and then we filled it. Then it was stable from the very beginning on. Then there was no degradation, which means that producing a bare copper heat pipe and then filling it might get some oxidation, and with this oxidation process, some wetting changes of the wetting characteristics.
It also depends whether you degas your working fluid and filter, otherwise the oxidation can be quite rapid.
So you think this is the main oxidation of the
primarily due to the oxidation.
So if I can add to that, it's not just oxidation, because we actually prepared ceramic surfaces super hydrophobic. And what you'd find is that after a couple of days, they stop being super hydrophobic, and it's water condensing inside the structures. So all your structures get filled in. So we put it back into a vacuum and it will become super hydrophobic. But if you pulled it out and left it in the open for a couple of days, it would stop being super hydrophobic. So it'll just pick up, water vapor from the atmosphere, and that will fill in all your structures. You lose all your structures.
So just to add to that, so it can be also absorption of organic molecules, volatile organic molecules. So may not necessarily be the surface degradation. It can be other aspects in the environment which causes the increase in the risk.
Sometimes in the impurity, because we use a very high flow loop in aluminum surface, where the velocity goes from 3 to 4 meter per second. And sometimes in the coolant, there is some impurities, even the small particles, and that actually keep off all this texturing, laser texturing, what we try to implement, and the whole surface, the performance deteriorates significantly.
Yeah, I think when I compared here the contact angle that we did with types of treatment, I think the laser, in our case, this was the laser texturing, so that you see these diamonds here. So these are fairly okay. They are comparable in our case to the chemical etching process. In fact, the other chemical etching
Generally, the
process,
hysteresis is high.
the hysteresis is a little higher. That was the only problem that we had. So it was about, in our case, hysteresis was about 20 degrees in the laser etching as compared to 2 degrees with the chemical etching process. But the durability was quite okay. Of course, we used a nanosecond laser. We can also use, picosecond or femtosecond laser if you want more fine structures and good control of the.
Sir, considering the commercial application, how do you comment on the cost effectiveness of preparing the surface plus maintaining it, considering this environment to which it is exposed?
So then, you need to compare it with what is the conventional way of improving the performance, right? So in this case, we are not doing anything additional to surface treatment. So chemical etching processes are not that expensive. We are not talking about femtosecond laser structuring. That needs a dedicated facility, of course. But chemical etching, I think you can do it with the help of these chemicals and a little bit of practice. And as far as the maintenance is concerned, as I said, we still need to understand what is the basic cause of the degradation of performance. And accordingly, we need to come out with a strategy how do we preserve these samples whenever we don't use them, or how do we fill them. I think this has to be a long-term process once we understand mechanisms behind the degradation.
So one last question. In one of your these flat plate heat tubes, you were talking about optimizing your filling ratio to 60%. Could you please explain how did you get that 60%?
60%. I didn't show those.
What are the
results.
parameters did you consider?
So we did a filling ratio study from 20% all the way up to 80%. So this is very common when we do any of these heat pipe studies. We need to understand the effect of what is the percentage of filling, and that result I didn't show you here, but we again checked the resistance of the device, and we found that 60% results in the lower thermal resistance. So you need an optimum balance so that you don't achieve dry out very early. At the same time, you should not overfill so that you don't condense properly. So you need a balance of filling ratio so that you don't reach an early dry out, as well as the same time you should have enough surface area and clearance available for the condensate to come down. So all these factors are part of this.
So, what is the effect of pressure on this? Any study you have done? So actually, if you want pressure on the,
so
if you want to extend this for thermal power plants where the absolute temperature will be very high, so how we can, you have done any experiment with higher?
So our primary objective was electronics cooling, thermal management. So the maximum temperatures that we are talking about are 80, 100 degrees. Of course, this is at much lower pressure, so therefore boils at much lower pressure. But then the evaporator temperatures are all limited to only 80, 100 degrees. But when you talk about power plants,
500 degrees,
1000 degrees or 1000 above 1000, right? So I don't know how these can be used for the evaporator tubes and things like that. Especially whether they are thermally durable at that high temperature is also another thing that can be studied.
you talked about optimizing the thermal performance, but sometimes using these techniques to optimize the heat transfer coefficient, or you decrease the resistance. But sometimes at the same time you reduce the maximum power that you can apply. So critically, you distinguish between heat resistance at a given flux or maximum heat flux? Because I saw sometimes both was increasing. Critical heat flux was increasing, and
Oh, that's with the pool
heat
boiling
transfer.
studies.
Yeah, that's what the pool boiling
Pool
studies.
boiling studies. Yeah, I mean.
Then I would say you were lucky that you increased both. Same method.
Yeah, I think you are right. Yeah, I mean, you can probably, there is some,
Did you go up to the maximum to the cryo?
we went maximum of 100 watt per centimeter square. I think I think probably it was not going to a dryout. But I mean, the point that we observed was there is a subtle increase in the critical heat flux with the mini channel surface. Probably at high heat fluxes, there is also an enhancement in the nucleation that is playing, so that these are the pathways. So there is an enhanced re-wetting of these surfaces because of the confinement of these small mini or micro channels that we are keeping. We continued this study with micro channels. This was with mini channels. We later continued this, and we found this enhancement was a little bit more higher with the micro channels, the critical heat flux. So definitely the explanation that I mean the enhanced nucleation characteristics can also be there. It's quite a possibility. Because if you look at lower wall superheats and low heat fluxes, when you plot it as function of wetted area, they are practically collapsing, saying it's only a fin effect, but definitely there is something beyond the fin effect at higher heat fluxes.
So, between condenser and evaporator, you maintain this adiabatic surface.
Yeah.
I just want to know, what do you mean by adiabatic?
It's
and
a
how
misnomer. Actually, it's a misnomer. It's definitely not the conventional way of calling adiabatic. So we don't insulate it. So we just it's called adiabatic because it's neither heated nor cooled. So the name, it's not. I mean, rather than saying just a neutral surface or something, we just call it as adiabatic. But we don't maintain it at perfect insulated condition. And especially in the context of a PHP, you cannot have a perfect insulation there because it's just conducting along the surface.
So, are you looking at any alternative liquids and liquid combinations?
Here we tested for both ethanol water and also ethanol water binary mixture, and we found this wettability modification to a great extent also works with the binary. So this is primarily with water. These surfaces are designated hydrophilic or hydrophobic. But when we also went with the binary fluid of ethanol water, 3:1 proportion, we found that still there is a improvement in the performance with ethanol water. But beyond that, we didn't use other dielectrics or other refrigerants, because then we need to go for kind of omniphobic surfaces and so on. So because obviously they are very low surface tension fluids, and whatever we call as hydrophobic or super hydrophobic will be just hydrophilic there. So in that case, the same performance enhancement will not work for refrigerants. We need to then look at that. There is also another area of prospective research.
So water is like this combination. Is it from the cost point of view to keep that cost down, or like is there any specific thing about water? Why it is?
Water is simply, if you look at the figure of merit of water, I think by far it is the best superior fluid because they have very high latent heat of vaporization, especially if you are using it for phase change, very high heat capacity. So therefore, there's no reason why we should not use water. Unless there are specific applications which call for using dielectrics, for example, in electrical, cooling, electric processor cooling, where you don't want to interact these electrical circuits with the water, so because they are also ionic. So you want completely non-ionized fluids. So there you use dielectric fluids and so on. But again, dielectric fluids suffer with having low thermal conductivity, low heat capacity and latent heat of vaporization is also low. And when you talk about wettability, like using changing the wettability also, like super hydrophobic will not work with dielectric. They are highly wetting fluid. So therefore, it's more challenging using dielectric fluid and improving the thermal performance using dielectric fluids is something that is of engineering challenge, I would say. Maybe Peter or Axel can add because they have been also trying using dielectric fluids.
Seems not much to add to that.
Okay, there are no further questions. I think someone should ask me to leave.
Thank you, Professor Arvind Pattamatta, for the engaging session. I request Dr. Axel Self to continue.
Sorry?
I request you to continue.
Thank you. So hopefully we'll do that for him.